All right, this is for section 6.1, matrices and system of equations. So we're going to introduce what a matrix is, most likely a new topic for most of you. A matrix can be used for a variety of things. We're going to see it here in section 6.1 to solve a system of equations. And that's why these two chapters are usually taught in the same unit. Chapter 5, which is solving systems of equations using elimination substitution. And then chapter 6 deals with matrices, which is another way you can solve systems of equations. So you can see the learning targets here, most important of which is this third one, solving a system of linear equations using what's called Gaussian elimination. So first of all, I've drawn a matrix right here. Zoom in here. So a matrix is really just a rectangular array of numbers is probably the technical definition. So it's really just a set of numbers, and the numbers are bracketed off using these bracket symbols here, and they come in a variety of sizes. But to determine the size of the matrix, you need to know the number of rows and the number of columns. So the rows are the horizontal components that go this way. So this matrix that I have drawn has two rows. Top row, or row 1, being the row 1, -5, and then the bottom row being the row 3, 2. Now the columns are the vertical part. So this matrix has two columns, column 1 being this column here, 1 and 3, and then column 2 being that column there, -5 and 2. So you always describe the size of a matrix right here as the number of rows by the number of columns. Always rows and then columns. So this matrix here that I've drawn, the size, or some textbooks call it the dimension, some textbooks call it the order of a matrix, is always rows by columns. So this one would be what's considered a 2 by 2 matrix. So your homework is going to start very simply by showing you some matrices and asking you to determine the size of the matrix. So you're just going to give the number of rows and then the number of columns for each one. So I've got 3 examples here. Part A, you can see there are 2 rows and 3 columns. So we call that one a 2 by 3 matrix. So if you want to pause and try the other 2. Part B is 3 rows and 2 columns. So this would be a 3 by 2 matrix. And then part C only has 1 row, 3 columns. So this one is a 1 by 3. So that's our first objective, really, is, let's see, state the dimensions of a matrix. Oh, one last thing before we move on. An individual number inside of a matrix is called an entry. So this entry right here, for example, the location of an entry is given by its row and column. So this entry is in row 1, column 2. So that's called the entry 1, 2. because it's in row 1, column 2. Anyway, let's move on. Where we're going to see the most usefulness from matrices is converting a system of equations into a matrix. It's what's called an augmented matrix. So right here, I've got a system of equations, 2 equations, 2 variables. To convert that into what's called an augmented matrix, you're just going to take coefficients of the x variable and form a column, and then the coefficients of the y variable, that forms a column. So there's going to be a 1 and a -2, and then the constants there, 8 and 14, form the last column. Some textbooks have a little dotted line to separate the coefficients of the variables from the constants after the equal sign. I don't believe our textbook uses a dotted line there, but just so you're aware, some textbooks do put a dotted line right there to denote augmented matrix. Now, when we have an augmented matrix, we perform what are called elementary row operations in order to start solving the system of equations within the matrix. And something to note, these are called elementary row operations because they pertain to a row of a column, sorry, a row of a matrix. So we can perform these operations on a row of a matrix, but not on a column. These operations don't work going up and down. They only work across the column or a row of a matrix. And these are the 3 row operations. You can add a multiple of one row to another row. You can multiply a row by a non-zero constant. And you can interchange or swap rows. You can make the top row become the bottom row, the middle row can become the bottom row or the top row. Sometimes it's helpful when solving a system of equations in matrix form to swap rows. So to practice these, I've got a matrix here, and I'm describing this row operation right here. 3 times row 2, and I'm going to add that to row 1. So this is row 2 right here. And what I'm going to do is multiply row 2 by 3. And then those are going to be added to row 1. And then the result of that is going to replace row 2. Now you're not going to see row operations written out explicitly like this in this form with words. You're going to see the same row operation written symbolically like this is how it's going to be described. 3 times row 2 added to row 1, that's going to replace row 2. So coming down here, three times row 2 in that first entry becomes a 3, because that's 3 times 1. And then if I add that to the entry in row 1, 3 times 1, whoops, let's get that back. 3 times 1 is 3, plus 2 is 5. So now I've got an entry of 5, and what it says is you're going to replace the entries in row 2. So that number 5 is going to go right here in row 2. Now I'm going to move over here and do 3 times 5, which is 15, and then that's going to add to row 1 entry. So 15 plus 4 is 19. And then it says, again, replace all the entries in row 2, so that's going to become a 19. And then here, 3 times negative 3 is negative 9. And then that negative 9 is going to add to 6 to make negative 3. And according to this row operation, I'm only replacing the entries in row 2, so all the entries in row 1 stay the same. So we're going to practice that again. Perform the indicated row operation. We're going to multiply all the entries of row 1 by 2, and then we're going to add that to the entries in row 2, and then that's going to replace all the entries in row 1. So ultimately, the only entries that are going to change are the entries in row 1. So the entries in row 1 are going to look different. The entries in row 2 and 3 are going to stay the same as they originally are. I'm just going to have new entries in row 1, and they're going to come from this row operation right here. So according to the first part of this, I'm going to take the entries of row 1, multiply them by 2, and then that's going to add to all of these entries in row 2. So right here, 2 times negative 5 is negative 10, and then you add negative 10 to 10, that makes 0, and then it goes in row 1. So 0. Now here, 2 times 2 is 4, and then 4 plus negative 3 is 1. And then here, 2 times negative 3 is negative 6, and then negative 6 plus 1 is negative 5. And finally, 2 times 3 here is 6, and then 6 plus negative 20 is negative 14. So those are called row operations. Just to practice and get used to the row operations, they're going to be given to you. You're going to just be given a set of row operations to perform. When we actually start using row operations to perform Gaussian elimination, which is our third learning target, you're going to have to come up with your own row operations in order to achieve an objective. And the objective is to write a matrix in what's called row echelon form. You start with an augmented matrix. So you can see I have an example here. This is just an augmented matrix. That would typically come from a system of equations. You start with an augmented matrix, and remember, each row represents one of the equations from the system of equations. So this top row is the equation 4x plus 8y minus 4z equals 4, and so on and so on. The other rows equal different equations. And you perform these elementary row operations in a certain sequence in order to change the augmented matrix into this matrix here, which is, this is row echelon form. This is a matrix in what's called row echelon form. And matter of fact, you may have some homework examples where you have to look at a matrix and determine if it's in row echelon form. And here's how you determine that. You see, starting at the top left, there's a 1, and then those 1s continue down in a diagonal. This is called the main diagonal of a matrix. Starts at the top left and goes down to the right. there has to be ones in the main diagonal. In order to be row echelon form, you have to have ones in the main diagonal. And then the other characteristic, you can see this little triangle I'm drawing. You have to have zeros beneath. So those are the characteristics of a matrix that's in row echelon form. You have ones along this main diagonal, and then zeros underneath, like that. And the reason it's so vital to it's called reducing a matrix to row echelon form, is these rows still represent equations from the system of equations that we originally, so remember, for example, this augmented matrix started as a system of equations. We performed elementary row operations to change the matrix into this form, but it still represents a system of equations. And this bottom row now, if it's kind of hard to see, but if I were to highlight this bottom row, there's a 0 for the x coefficient, meaning there's no x. There's a 0 for the y coefficient, meaning there's no y. But there's a 1 right here for the z, and then there's a -2. So that bottom row right there tells us that the value of z is -2. And then if we look at this middle row, again, oops, let's get that back. The x coefficient is 0, so there's no x, but the y coefficient is 1, so we have 1y, and then we have 4z equals -7. But we know that z equals -2, so 4 times -2 is -8, so that turns into y minus 8 equals -7, and then if you add 8 to both sides, you get y equals 1. And then we can work our way to the very top row of row echelon form matrix, and using the coefficients there, we get x plus 2y minus, I'm looking at this -1 here, that's -1z, or just minus z equals 1. But then we can use the fact that y equals 1 and z equals -2 to write this as x plus 2, and then minus z means minus -2, that's plus 2 equals 1. 2 plus 2 is 4, subtract that on both sides and you get x equals -3. So once a matrix is in row echelon form, you can use that to solve for the variables, and we get a solution here of -3, 1, -2. So now let's look at this exact same problem from start to finish, starting with the system of equations. This is our last learning target. And like I said, this is the main one for this section. Using Gaussian elimination and matrices to solve a system of equations. So I've got some steps here. First step is to write the system of equations as an augmented matrix. Second step is to use row operations to reduce the augmented matrix to row echelon form. And once it's in row echelon form, like I just showed you, you can backward substitute. Start on that bottom row, solve for z, then use the middle row to solve for y, and then use the top row to solve for x. It's called backward substituting. So I've got that exact same system of equations as in this above example. We started with the augmented matrix, but we're going to go from start to finish. So the first step is to write the system of equations as an augmented matrix. And then we need to perform row operations to reduce this matrix to row echelon form. And there isn't one specific right way to always do this as far as an order, but there's a general direction that you should head as far as your strategy. And it's as follows. If you remember the characteristics of row echelon form, the main diagonal here should be 1s, and then the entries beneath them here should be 0. And here's how you should proceed to do that. This first entry should be a 1, and then you get the entries beneath it to be 0. Then you move on to this entry and get that to be a 1, and then you get that entry to be a 0, and finally you get that entry to be a 1. And it is going to be in your best interest to try to do it in that order. Again, let me repeat. First order of business is to get that to be a 1, and then get both of these to be 0. Then try to get that to be a 1, and then get that number to be a 0, and finally get that to be a 1. And the only row operations you can perform were what we talked about just a few minutes ago. Where'd they go? These row operations right here. You can add a multiple of one row to another row. That was what we did here. We added a multiple of row 2 to row 1, so that's adding a multiple of one row to another row. We can also multiply a row by a non-zero constant. And if you're trying to get an entry to be 1, that's usually the row operation that's going to be the easiest to do, is that second row operation. Multiply a row by a non-zero constant. So for example, if I multiplied the whole row by 1/4, every entry would be multiplied by 1/4, which would turn that entry into 1. And that's called multiplying a row by a non-zero constant. So the way that you are going to show this, anytime you're going to do a row operation, create a new matrix, and then describe that row operation as follows. I'm going to do 1/4 times row 1, and that's going to produce a new row 1. And then once you've described what row operation you're doing, go ahead and rewrite the matrix after performing that row operation. So what this is doing is going to multiply every entry in row 1 by 1/4. So that makes 1, 2, -1, and 1. And this row operation only affected row 1, so row 2 and row 3 are going to remain unaffected. So that was our first order of business. We got that to be a 1. Now we focus our attention on those two entries beneath it, or in this case, these two entries here. Those need to turn into zeros. The best way to accomplish that is to use row operation number 1. Let me go back again here. To get entries to be 0, your best bet is to use this row operation, adding a multiple of one row to another. And the best way to do that is, now that we've gotten this entry to be a 1, I'm going to focus now on this entry right here that's supposed to be a 0. The only number you can add to 3 to make it 0 is -3. So luckily I've got a 1 right here. If I multiply that by -3, so -3 times row 1, and then added that to row 2, which is this number here. So -3 times row 1 would make that a -3, and then if I add that to row 2, that's going to make a 0, and I want that 0 to go into row 2. So that's going to be the row operation I'm going to do is, let me describe that over here. I'm going to multiply row 1 by -3, which is going to make a -3 right here in particular. It's going to multiply the whole row by -3, and I'm not really concerned about the whole row. I'm concerned about making this -3 so I can add it to that +3 to make 0. And you're thinking, well, you just made a 1 right here, so why would you want to change it to -3? It only changes to -3 so I can add it to row 2, and then I'm going to replace the entries in row 2, meaning row 1 is going to stay the same so that this 1 I just created doesn't change. So let's see what that looks like. This entry is in row 1, so according to this row operation, it's going to be multiplied by -3. So -3 times this 1 is -3, and then added that to that 3 makes 0. Now, -3 times that entry in row 1 is -6, and then add that to 8. -6 plus 8 is 2. Now, -3 times this entry is 3, and then 3 plus 5 is 8. And then -3 times that entry right there in row 1. -3 times 1 is -3. -3 plus -11 is -14. So you can see I've got a 0 right there where I needed it. Now, this entry here also needs to be a 0. And as long as you're going to do a row operation that's affecting a different row, this operation only affected row 2. Now I need to affect row 3. So I can describe another set of row operations here as long as it's affecting a different row. So this is going to now affect row 3. And remember, the task is to change this to a 0. Now, the only way I can change this to be a 0 is to add 2 to it, because remember, I can't multiply a row by 0. I can only multiply a row by a non-zero constant, so I can't just multiply it by 0. I have to add a multiple of another row to it. And the only number to add to -2 to make it 0 is +2. So I'm going to go back up to here. If I multiply row 1, so if I take row 1, and I'm only looking at this first entry because I'm only looking at this first entry here. If I multiply row 1 by +2, and then add that to row 3, which is this entry, that's going to give me a 0. And then I want to replace that 0 in row 3. So that's going to be my next set of row operations. It's 2 times row 1 so 2 times row 1, which is going to make this a 2, but then I'm going to add that to row 3, so 2 times row 1 plus row 3, and that's going to give me new entries in row 3. So let's see what that looks like. This first part says 2 times row 1, so that gets multiplied by 2. 2 times 1 is 2, and then I add that to row 3. 2 plus -2 is 0. And then following the same thing, 2 times row 1 here, 2 times 2 is 4, and then 4 plus 1 is 5. And then here, 2 times row 1, so 2 times -1 is -2. -2 plus 12 is 10. And finally here, 2 times row 1 is 2. 2 plus negative 17 is negative 15. And both of these row operations affected row 2 and row 3 only, so row 1 stays the same as it was right here. Okay, so you notice I have a 1 here, and then these entries became 0. So now we'll have to focus my attention here, because remember, along this main diagonal, I need 1s. So that 2 needs to be a 1. And the best way to get an entry to be a 1 is to multiply by its reciprocal. So since this entry is in row 2, I'm going to say row 2, and then if I multiply 2 by 1/2, it's going to turn that row, it's going to turn this particular entry, is the one I'm interested in. 1/2 times 2 is 1. And I want that 1 to be in row 2. So this row operation is going to affect row 2. And it needs to happen to all of the entries in row 2, even a 0. So 0 times 1/2 is still 0. 1/2 times 2 here is 1. 1/2 times that 8 is 4. And 1/2 times negative 14 is negative 7. And that row operation only affected row 2. So row 3 stays the same. And row 1 stays the same. Okay, so I've got 1, and then the zeros here. I got a 1 here. And remember the order now. The entry underneath it needs to be a 0. So now I'm focusing on this 5. That 5 needs to be a 0. I can't multiply the whole row by 0. That's not going to work. You can only multiply a whole row by a non-zero constant. So the best way to get a number to be a 0 is to add its opposite. So if I wanted to add negative 5 to it, that would make it a 0. So what I'm going to do is use that 1 that I just created. If I multiply row 2 by negative 5, that's going to make a negative 5 right here. And then if I add that negative 5 to that 5, that's going to make 0. So what I'm going to do is say negative 5 times row 2. That's going to multiply the whole row 2 by negative 5. And then I need to add that to row 3. And then that's going to make that a 0 right there. And then I want the 0 to be right there in row 3. So this row operation is going to make a new row 3. Okay. And this row operation has to happen to the entire row starting at the beginning. So right here, negative 5 times 0, well, negative 5 times 0 is 0, and then 0 plus 0 is 0, and I'm putting it in row 3 because it says to put it in row 3. And then negative 5 times that entry in row 2 is negative 5, and then negative 5 plus 5 is 0. And then negative 5 times that entry is 20, negative 20 rather, and then negative 20 plus 10 is negative 10. And then negative 5 times that entry is 35. And then 35 plus negative 15 is 20. And this row operation only affected row 3, so every other row stays the same. Now we're almost there. I've got 1 and then zeros. Then I've got 1 and a 0. Only thing that's remaining to be row echelon form is that should be a 1. And best way to make an entry 1 is to multiply by its reciprocal. And this entry is in row 3, so I want to change it to 1. I'm going to multiply it by its reciprocal, negative 1/10. This is the entry I'm talking about. I want to change that into 1, so I'm going to multiply it by its reciprocal, which is negative 1/10. And that's going to replace row 3. And it's got to happen to all the entries. So starting at the beginning, negative 1/10 times 0 is 0. Negative 1/10 there times 0 is 0. Negative 1/10 times 10 is positive 1. And then negative 1/10 times 20 is negative 2. The other rows stay the same. Now we finally have row echelon form. We have 1s along the main diagonal and then 0s right here. Once it's in row echelon form, we stop using Gaussian, well, the whole process is called Gaussian Elimination, but we can stop using row operations and start to backward substitute, because now this bottom row represents an equation. There's no x variable, there's no y variable, but there is z, and it equals negative 2. This middle row, there's no x variable, but there's a coefficient of y. It's 1, y plus 4z equals negative 7. But we know that z equals negative 2 right here. 4 times negative 2 is negative 8. And then if we add 8 to both sides, we get y equals 1. Now if we move up here, there's a 1 coefficient for x. There's a 2 coefficient for y. There's a negative 1 coefficient for z. But we know that y equals 1. And we know that z equals negative 2. So this is x plus 2. And then negative 1 times negative 2 is positive 2. This makes 4, so subtract 4 and you get x equals negative 3. So we have the value of all 3 variables. To be able to go back to the very beginning where we started with a system of equations right here, and we now know the solution, and I just should have transferred it over. It was negative 3, 1, negative 2. And it's never a bad idea to check your solution. For example, if that's negative 3, if that's positive 1, and that's negative 2, we get 6 plus 1 minus 24, and that should be negative 16. So we've got 7 minus 24, and that does equal negative 17. So it checks out. You'd be best to check it. It should satisfy all 3 equations, but that's called Gaussian elimination. And I guess I should have started with this. This is not meant to be a shortcut to solve a system of equations. The quickest way to solve one by hand is what we learned in Chapter 5, elimination or substitution. Why are we learning these new methods then? This is how computer systems can solve system of equations. A computer system doesn't really understand system of equations, but it does definitely understand arrays of numbers. A computer system can solve an array of numbers instantaneously, pretty much, using pretty much this process here. So this is not really meant to be a shortcut to be done by hand. You're just learning the process of how a computer system would solve it. I'm going to do a couple more examples just to practice. And with practice, this process can become quicker, but just know, and again, I apologize, I should have front-loaded this discussion with this, that Gaussian elimination is not a quick process. It takes time, you got to go slow, you got to be careful. If you speed through it, if you try to rush through it, you're going to make mistakes. Your answer is going to be way off. You got to be patient. You just got to go slow, methodical, and carefully. So let's look at another example here. Okay. So we have another system of equations here. We're going to solve this system using Gaussian elimination. Again, keeping in mind this is not a shortcut, but if the directions specify to solve using Gaussian elimination, then that's the process that needs to be shown if this were an exam. Otherwise, there would be no credit awarded for the problem. So make sure you read the directions. If it just says solve the system of equations, you can solve it however you want. But if it says solve using Gaussian elimination, you do have to follow these steps we've been outlining here. So step one, it was to make the augmented matrix. Okay. Now the main portion of this problem is then going to be reducing the matrix to row echelon form. Now remember the process you want to go, and it does need to be done in this order. You want to get this to be a 1, and then the numbers beneath it need to be 0. So do this first, get that to be a 1, then get this to be a 0, then you get this to be a 1, and then you get this to be a 0, and then you get this to be a 1. It needs to follow in that pattern. So if you remember the last problem, in order to get this value to a 1, what we did was multiply that whole row by the reciprocal, which would definitely make that value turn into a 1. The problem, well, it's not really a problem. The thing I want to make you aware of is that would create a fraction here of 3 halves, 1 half, and 13 halves, which isn't going to make the problem impossible to solve. It complicates a little bit when you have a lot of fractions in there. So I'm actually not going to do that. One thing I noticed is there's already a 1 right here. And if you recall, one of the elementary row operations that you can do is you can swap an entire row. So I can take this whole row and move it up here, and then take this middle row and move it down here. It's called swapping rows. And by swapping that row, that's going to put this 1 up there, and then I can just multiply it by -1 to turn it positive. So I'm actually going to do that. My first row operation is I'm going to swap row 1 and row 2. So row 1 is going to become this middle row here. And then row 2 is going to become that one there. And I didn't do anything to row 3. Okay. Now I'm supposed to have a positive 1 there. So if I multiply that whole top row by -1, that'll make that first entry positive 1. So what I need to do is -1 times row 1 is going to give me a new row 1. So it'll be +1, -2, +5, -6. Row 2 doesn't change at this point, and row 3 does not change at this point. So now that I've got a 1 right here, remember my next step or task is to get those to be zeros. And you can't multiply a whole row by 0 because that's just going to turn the whole row into 0. You don't want that. So the only thing that's going to change this number 2 into 0 is to add -2 to it. So if I take this top row and multiply it by -2, that's going to make a -2 right here, which I can then add to that 2 to make a 0, and then I would just place that 0 in row 2. So what I need to do then is I'm going to take row 1, multiply it by -2, add that to row 2, and then place that value in row 2. So this whole top row is multiplied by -2. So -2 times this 1 is -2, and then -2 plus 2 is 0. -2 times that -2 is 4, and then 4 plus -3 is 1. -2 times 5 is -10, and then you add -10 to -11, or -1, and you get -11. And then -2 times -6 is 12, and then 12 plus 13 is 25. Okay. Now, I also need to change, here we go, sorry. This is also supposed to be a 0. So I can do a similar thing. If I multiply now this top row by -5, that's going to put a -5 right here, and then if I add that -5 to the +5 and then put it in row 3, that would give me a 0 right there. So what I need to do now, and since it's affecting an entirely different row, this operation affected row 2, I'm going to describe one that's going to affect row 3. So I can use this space down here to describe a new row operation. I'm going to do -5 times row 1 now, and add that to row 3, and that's going to become a new row 3. So -5 times 1 is -5, -5 plus 5 is 0, and then -5 times -2 is 10, and then 10 plus -1 is 9, -5 times 5 is -25, and then -25 plus -1 is -26, and finally -5 times -6 is 30, and then 30 plus 49 is 79. Okay, row 1 is going to stay the same. So we got that to be a 1, we got these to be zeros. The next step would be to get this to be a 1, but it already is, which is nice. So now the next step is to get that to be a 0. And again, you can't just multiply that whole bottom row by 0, because that's just going to turn every value into 0, which you don't want. So the only thing I can do to that 9 to make it 0 is to add -9 to it. So if I multiply this second row now by -9, that's going to put a -9 right there, which I can add to row 3, which is what I want to do. So this row operation is going to be -9 times row 2. I'm going to add that to row 3, and that becomes a new row 3. Okay. And technically it has to be done to every entry in the row. So -9 times 0 is 0, and the 0 plus 0 is 0. And then -9 times this 1 is -9, plus 9 right here is 0. -9 times -11 is 99. And then we have 99 minus 26. It looks like 73. And then -9 times 25. Okay, so we get the calculator. -9 times 25. So that's -225. But then we add that to the entry in row 3, which is 79. So -225 plus 79 equals negative 146. Okay, so we're almost there. The next step is to get that to be a 1. So if I multiply the whole row by 1 over 73, that should do it. So row 3 is going to be multiplied by 1 over 73. That's going to give me a new row 3. So this whole row is multiplied by 1 over 73. So right there, that's going to give me a 0. And then multiplying here is going to give me a 0. Multiplying here is going to give me a 1. And then multiplying there, negative 146 multiplied by 1 over 73 is negative 2. Row 2 stays the same. Row 1 stays the same. And let's take a quick look. We have 1s along that diagonal there, and then 0s underneath. So we are in business. That's row echelon form. Once it's in row echelon form, we can begin the process of backwards substituting. So this bottom row represents an equation. We only have a coefficient of z, so that's 1z, or just z equals negative 2. And we can move up a row. There's no x variable because there's a 0 coefficient, but we have y minus 11 equals 25. Sorry, y minus 11z equals 25. This negative 11 is a coefficient for z. Now we know that z equals negative 2. So if we multiply that negative 11 by negative 2, we're going to get y plus 22 equals 25. If we now subtract 22, we get y equals 3. Now we can move up here. That row represents an equation. Now we have coefficients for all 3 variables now. So we have 1x minus 2y plus 5z equals negative 6. We know that y equals 3. And we know that z equals negative 2. So if we make those substitutions, we're going to have x and then negative 2 times 3 there is negative 6. And then 5 times negative 2 is negative 10. And then we have x minus 16 equals negative 6. If you add 16 to both sides, you get x equals 10. So we have a solution of 10, comma 3, comma negative 2. Now I'm going to move this way back to the beginning here. There it is. And again, never a bad idea just to check. We've done so many steps, so many mathematical operations. It is relatively easy to have made a simple mistake somewhere. So if x equals 10, then that's going to give me 50. And then minus 3 minus negative 2. So 50 minus 3 is 47 plus 2, that equals 49, which is what it should be. So it checks out in that bottom equation. You should check them out in all 3 because a solution should satisfy all 3 equations. But for the sake of time, we're going to call that one good. Okay. If you recall from section 5.2, when we solved systems of equations with 3 equations and 3 variables, there were some special cases. We could have no solution or infinitely many solutions. And the same thing will happen if you're solving using Gaussian elimination, we could still have a case of no solution or infinitely many solutions. So I want to show you what that looks like. So we're going to solve this one using Gaussian elimination. So the first step is to create our augmented matrix. Now, taking a look at that middle equation, there's no y variable, so you have to put a 0 right there for the y coefficient. Okay, so we have the augmented matrix. I notice there's a 1 right here, and where I really want to have a 1 is right there. So I'm going to go ahead and swap row 3 and row 1 as a first step. So swap row 1 and row 3. So this bottom row here, I'm going to move up to the top. And then this top row here, I'm going to move to the bottom. Middle row stays the same. Now I want these here to be zeros. So I'm noticing here, if I just add these two rows together, row 1 plus row 2, that's going to give me 1 plus -1, which is 0. And then I could just place that 0 right there in row 2. So what I'm going to describe here is row 1 plus row 2, and that's going to give me a new row 2. So if I add these two, I'm going to get 0. If I add those two, 1 plus 0 is 1, so it's going to give me a 1 right there. If I add these two, that's going to give me a -3. And if I add those two, that's going to give me +1. Now I also want this to be a 0. The only thing I can add to -3 to make it 0, +3. So somehow I want to add +3 to that number. So I can come up here to this top row and multiply the whole row by 3, which puts a 3 right here, which I can then add to that -3 to make 0. So what I just described is row 1, I'm going to multiply that by 3, then I'm going to add that to row 3, and then I want those values to go into row 3. So what that's going to look like is I'm going to multiply by 3 right here. So 3 times 1 is 3, and then add that to -3, and I'm going to get 0. And then 3 times 1 here is 3. 3 plus -5 is -2. 3 times -10 is -30. -30 plus 36 is 6. And then 3 times -4 is -12. -12 plus 10 is -2. And then row 1 didn't change, so it stays the same there. Now I've got 1, 0, 0. Then you move over here, and that's supposed to be a 1, which it already is. Now this is supposed to be a 0. So the only thing I can add to -2 to make it 0 is +2, and I can use this 1 right above it to accomplish that. So if I multiply this 1 right above it, if I multiply that 1, matter of fact, that whole row, if I multiply it by 2, that's going to put a 2 right here. And then if I add that 2 to -2, that's going to give me 0. So what I just described is row 2 is going to be multiplied by 2. I'm going to add that to row 3. That's going to give me a new row 3. So 2 times 0 is 0, and then 0 plus 0 is 0. And then 2 times 1 is 2, and then 2 plus -2 is 0. 2 times this -3 is -6, and then -6 plus 6 is 0. And then 2 times 1 is 2, and then 2 plus -2 is 0. And this is why this is considered a special case. We have a row of all zeros in the bottom. It still does represent an equation, but since there's no variables, the left side of the equation is 0. And then after the equal sign here, the constant is 0. So we have a statement of 0 equals 0. We've seen this before. We've seen it a couple times. 0 equals 0 means infinitely many solutions. So you just need to make a mental note or actually write a note to yourself on your notes. But if you have a row of all zeros, that's infinitely many solutions. Now we're not quite done with this problem because we need to parameterize like we did in chapter 5. I just want to make you aware of the other special case. If this were a different problem, and let's say we had 0, 0, 0, and then a number like 7, for example, then we would have a statement of 0 equals 7. That's not a true statement. If that were the case, you would write no solution. But for the problem we are working on, we have 0 equals 0, which is an indication of infinitely many solutions. And since we have 3 variables, x, y, and z, the convention that we talked about in section 5.2, when we're parameterizing variables, is to let z equal t. And then we go back up to this middle row. Now we're just backwards substituting like we did in all the other problems. That middle row represents the equation 1y minus 3z equals 1. Now we can make a substitution here for z. Z is equal to t, so now we can say y minus 3t is equal to 1, and I want to get y by itself, so I'm going to add the 3t over and get y equals 3t plus 1. So we have 2 of the variables solved. We have z equals t, and we have y equals 3t plus 1. Now we just need to find x. So we get x from this top row. We have x plus y minus 10z equals -4. And now we make the appropriate substitutions. For y, I'm going to put in that 3t plus 1. And for z, I'm going to put in that t. So I have x plus 3t plus 1 for y minus 10. Instead of 10 times z, it's 10 times t. And that equals -4. Now I'm solving for x, so I just need to move all the other terms to the other side. The only reason I had these parentheses in here is to make a substitution. There really doesn't need to be parentheses if there's no exponent here or if there's nothing to distribute. So it's really just x plus 3t plus 1 minus 10t equals -4. If I combine some like terms here, I'm going to have x minus 7t plus 1 equals -4. I can subtract a 1, and I get x minus 7t equals -5. And then I can add the 7t over and get x equals 7t minus 5. So then the parameterized solution, instead of x, y, z, the value for x was 7t minus 5. The value for y was 3t plus 1, and then the value for z was t. So this is what you would circle as your solution. So that finishes up section 6.2. The most important part of this section was learning how to solve a system of equations using Gaussian elimination. And in some cases, there's a special case where you're going to have no solution or infinitely many solutions like this one. And you have to parameterize your solutions if you have infinitely many solutions. And like I said, Gaussian elimination is not a quick process. You have to go slow. You've got to be careful. Just be patient and take your time.